Hi everyone, and welcome to Erik's Electronics Workbench. So the project on the bench today is this Simpson 260 Series 6. Now this meter was donated to the channel by a viewer. He said he no longer needed the meter, but that it's not accurate. It seems to have a problem. So let's see what it takes to put the meter back into service. And if you're interested in how these meters work, stick around because I'll go through the schematic and I'll explain how the meter actually functions. So let's get started. So some accessories were included with the Simpson 260, this leather case and the test probes. It's definitely nice to have these, but for now I'll just set them aside. And let's take a look at the meter. So it looks to be in nice cosmetic condition. I don't see any damage to the case. There's no scratches or cracks. The glass is in good condition. The face of the meter, the dial, is in very nice condition as well. Handle's in good shape. The switches rotate smoothly. Nothing's binding up. The 0 ohms potentiometer turns very easily. So for the age of the instrument, it looks to be in nice external condition. Now, the way that you see this meter is exactly how I received it. I haven't done anything to it yet. I haven't opened it up. I haven't tested it. The only thing that I did do is that I took this cover off the battery compartment because I was curious to see if there was any corrosion around the batteries. And I'm happy to report that it's very clean. So if I turn this over here, you can see the battery compartment looks like factory new. So there's never been any kind of corrosion in here. And so many of these meters were damaged over the years because of leaking batteries. And earlier series of these meters, the batteries were installed right around the circuit board, so if they leaked, damaged the board and the components. So in this series and later series, the batteries are in this separate compartment, which of course is easier to change the batteries, but it contains any leaking more to this area, but it can still cause a lot of damage. And there's a little opening where the wiring passes through, and if there's enough corrosion and leaking, of course, that can still work its way down into the meter. And a lot of times these meters are stored upright, and of course the corrosion will work its way down. But everything looks very clean in here, so that was good to see. Now this fuse right here is supposed to be a 1 amp fuse. I'll just set this down here, and you can see the fuse that was installed is this fuse right here. So just touch this up and you can see what caught my attention when I was looking inside that battery compartment is the size of the element in that fuse, and you can see how wide the element is. I thought, that doesn't look like a 1 amp fuse. So I took it out and took a closer look. And this is actually a 15 amp fuse, so someone was maybe mistaken and saw the 1 and not the 5. I'll turn this back over again here. So I installed the correct 1 amp fuse, but unfortunately with a 15 amp fuse in here, that's not going to provide any kind of protection. So hopefully the meter hasn't been damaged because of that 15 amp fuse. Now, a common reason that the fuse goes away is because, let's say this is in the current measuring ranges, so 500 milliamps or 100 milliamps and so forth, and then you take the test probes and you measure AC line voltage or across the battery or something like that, or a power supply. Of course, it just takes that fuse out for protection because, basically the meter has a very low impedance at that point. If this 15 amp fuse was in there, something else is going to go up in smoke because the switching, the wires, resistors, things like that in here would easily be damaged, and the 15 amp fuse would just sit there. Now, the 15 amp fuse, that got put in place because the fuse prior to that would have been damaged and maybe there was an overload condition. So hopefully when we get this meter apart, we're not going to see extensive damage because of the wrong fuse or some kind of an overload or something like that happening. So we'll find out when we get inside the meter and see what's going on. Again, all I know about the meter is that it's supposedly not accurate. Now, the first thing that I want to do with the meter is just take some resistance measurements using my digital multimeter and get an idea if the multiplier resistors are in good condition. And the calibration on this meter, you can tell a lot by the calibration by taking a measurement from the common terminal jack over to this jack that says 50 microamps and then 250 millivolts. So let's take that measurement with the resistance and we'll kind of see what's going on with the meter just while it's all together and sitting here, and then we'll open up the meter and take a closer look inside. So let me grab the digital multimeter and just bring it over here. Get this zoomed out a little bit. You can see everything. That's started up. So I'm going to grab these test leads right here. And that fuse that we were looking at, it's in line with the common jack, so pretty much all the measurements that you make, that fuse is always in the circuit, other than when you measure with a 10 amp. So there's a minus 10 amp and a positive 10 amp jack, and there's no fusing on that 10 amp shunt. So the fuse, has no protection for that higher current, but for all the other measurements, the fuse is certainly in the circuit for protection. All right, so what I'm going to do is just plug this in over here. Let's get this set to resistance. And on this particular meter, it has a low power setting for the ohms, and I want to use that. And we're going to start with the 10K ohm, which will put that at 10 microamps. I don't want to put too much current through the meter to start with. I don't want to cause any damage. So let's just plug this in right here. All right, there we go. So you can see a little bit of indication on the meter. But right away you can see that's reading just shy of 2,000 ohms, 2K ohms. And that's actually not right. Okay, that should be reading very, very close to 5,000 ohms. Make sure you can put this all the way over here. You can see that. So I'm going to grab the schematic. Now, in just a little bit, after we go through some of these measurements and we look at the meter and take it apart, I'm going to go over the schematics and in more detail. But for now, let me just show you something on this schematic, a little bit about what I'm measuring here. So right now, this portion of the circuitry right here, you have the 50 microamp meter. This actually has a full-scale deflection of 48 microamps. All right, so just a little bit under 50 microamps, so 48 microamps. And then you have this resistor here, 200K ohm. It's an adjustable resistor inside the meter for calibration, and it's shunting across this meter movement. And then you have this 5K ohm adjustable resistor as well. And so these two adjustable pots are for the calibration. From this point to this point, so this entire circuit right here is supposed to be 5K ohms, all right? And then the measurement that we're making right now is electrically just going from this side of the meter to this side of the meter. So nothing over here is actually in the circuit at this point. And we're not seeing 5K ohms, we're seeing about 2K ohms. So that tells us right now that the calibration is way off, and there maybe is even a failed component of some sort. But it is good to see that the meter has deflected, so the meter movement does work, and that's nice to see. And the reason that I'm doing this, kind of sneaking up on the meter and taking these measurements, I don't want to put voltage on the meter to start with, because if multiplier resistors are damaged or there's other problems going on, I don't want to damage the meter movement or other components. So again, this is kind of a way to take some measurements and just sort of sneak up on the meter and get an idea of what's going on. So we can see right now, though, there is a problem. So it's definitely not going to be accurate, when you're seeing 2K ohms at this point. Now, next thing I'll do is just move this over here. So I'm going to go down to, actually, let's move this over to the 1 volt setting first. That's right there. And I'm just going to go over here to auto range. Okay, so this is on the 1 volt setting, and we do see a little bit of deflection as well. But you can see right now we're getting about just shy of 17K ohms. Now, this meter has a 20,000 ohms per volt rating on the DC measurement and 5,000 ohms per volt on AC. Now, what does that mean? Well, basically, you just take the full scale reading, so in this case we're on the 1 volt full scale, and you multiply that by 20,000 ohms. So 1 volt times 20,000 ohms is 20,000 ohms, obviously, and we're not getting that. So that tells us right there that there's a problem not only in the meter circuit, but perhaps elsewhere in some multiplier resistors. We're starting to see some other issues going on here. All right, so again, 20,000 ohms per volt. Going back to this first setting, it was on 250 millivolts or 50 microamps. And if you take 250 millivolts and multiply that by 20,000 ohms, you get 5,000 ohms. And again, that's what we should have been seeing there, and we weren't getting that reading as well. Okay, so moving this over to this jack right there. So I'll leave this switch in the same position. So now this is 2.5 volts full scale. We're still getting a little bit of deflection on the meter. Actually, I can go over here and turn this low power setting off. So on a 2.5 volts full scale, that should be 50,000 ohms. So 2.5 times 20,000 is 50,000. So we're shy of that, so there's a bit of a problem there. but we are seeing an increase in resistance. So the multiplier resistors are in circuit, and we know that this switch is having an effect, through the switching and the contacts. It's not a complete open circuit for that matter, but it's definitely not the right readings. Now on 10 volts, 10 volts should be 200 k ohm, 200,000 ohms. We're very close to that value, but perhaps a bit off there. So this is in megohms right now, so 0.2. So that's just a little bit over 200 k ohms. Let's go to 50 volts. So on 50 volts, it should be 1 megohm, and we are at 1 megohm and some change. And really, that should probably sit closer to 1 megohm, so that's not quite right. But the multiplier resistors are certainly doing something, because the resistance is increasing as I increase the voltage ranges, so that's good to see. So 250 volts, that should be 5 megohms. It's just shy of that. It's close, but down just a little bit. Go to 500 volts, that should be 10 megohms. And yeah, it's 10 megohms and some change, but probably should be a bit closer than that. That's really off by a little bit more than you'd want to see. And then what I need to do is move this over here to the 1000 volt jack right there. So that should be 20 megohms, and it's a little bit on the high side. So yeah, the numbers, things are off a little bit, not really where they should be. So no surprise that if you were to take an actual voltage measurement, it really wouldn't be all that accurate. Now, all right, so let's take a look at the ohms range and see if we have any activity there. So for that, let me just grab just different test probes here, test leads. So come over here. So let's go to resistance times 1, and I'm just going to touch these together. So we have full scale deflection right there, and this should 0. Yes, it does 0, but this is turned down all the way, almost all the way, but it does 0 out. So let me grab a resistor right here. I think there's probably something in here. This one up here. So here's an 8 ohm power resistor. Let's try this. Not accurate at all on that. So you can see with 8 ohms, it still goes to full scale deflection. And 8 ohms really should be reading over in this area right here. So I have a problem going on there with the resistance measurements. Let's take a look at, let's go here to resistance times 100, back to zeroing. Well, it doesn't really want to 0, so there's beyond full scale, and if I turn this all the way down, it's still a little bit high right there, so something's not quite right with being able to even 0 it. Grab another resistor up here. I think this one might be a 300 ohm. Yes, it is. So here's a nice 300 ohm power resistor. Yeah, that's the same problem. It just goes to full scale. So that's definitely a problem there. And let's take a look here. R times 10,000. Oh, that pegged the meter over all the way there. That went full scale when I clipped the leads together. Yeah, there's really no point in even trying to take a measurement there. That's completely off the scale, and I can't 0 it at all. So that's definitely not working. So definitely some problems going on with the resistance measurements. Let's go ahead and get this meter opened up, have a look around inside, see exactly what's going on, because we can definitely know that there are some issues. So we'll grab the screwdriver here and turn this over. Get this battery out of there, and the 9 volt off of there. So there's just 4 screws to get the cover off of here. So if you've watched this channel, you may have seen a Simpson 260 already, and this looks familiar, yes, I did do a Simpson 260 repair. That was a Series 4. And again, this is a Series 6. All right, let's see what we have going on here. Should just open up. May not be all the way screwed there. There we go. Perfect. All right. It has that antique electronic smell. A good old electronic smell that you get with these vintage devices. This is zoomed in a little closer here. That touched up a little bit. All right, so what do we see in here? Oh, well, I see something on it right here. This red wire right there is smashed flat. See that right there? That wire is pinched. So that's going to need some attention. That's on the 9-volt battery snap. So that wire got out of place and got pinched right here in the housing. So, but that's a minor thing. That's not a big deal. It must be working because the 9-volt battery comes into play in the highest resistance setting, and we did have activity, so it's probably not cut all the way through. It must be making some connection through there. All right, so well, right here, these resistors right on the corner are not original at all. These look like some kind of maybe a metal oxide resistor. Definitely not original. So that's a problem. So something's been worked on there. These diodes right here, so these are the 2 rectifier diodes for the AC voltage. And they've been, it looks like they were maybe cut out of the circuit and then replaced, or maybe they were taken out for testing or something. But there's some solder where they've been reattached. So it looks like they were snipped off right there and then reattached back on there. So, you know, that should maybe be cleaned up a little bit there. So these are the calibration potentiometers right here. So these 2 are for the AC volt ranges, and then these are the 2 that are for the meter itself, that 5,000 ohms that I was talking about. One's 5,000 ohms, the other one is 200 k ohm. Let's see here. And actually this one looks like it has the factory seal on it. I don't think it's ever been turned or adjusted. This one has. This is out of place. This is turned all the way to one side right there. So someone's been in here turning things and messing around with some adjustments. So these resistors, these look original here. Don't see any problems. None of these look overheated. Oh, this is a big problem right there. Look at that. That resistor right there. Get this touched up. So that's serious overheating going on in that resistor. So that's going to need some attention right there. This resistor right here kind of looks like it's up off the board, but it may be original. It looks like the right kind of resistor. It's just kind of like it's been pushed or moved around there. These resistors here don't look original. This resistor right there and this one, those look like the old style carbon composition resistors. Definitely not the kind that would have been used in this meter, so I think those have been replaced. To check this capacitor, see if it's in good condition. That's an easy thing to replace if necessary. I can check that for leakage and correct value. Oh, I see something going on here. You see that under the board right there? That's definitely not original. So it looks like there's a wire it's tagged on. It looks like it's in parallel with this top resistor right here. See that? So that's definitely a problem. I don't know why someone would do that. Maybe this resistor failed. If you have a resistor that fails or any component that fails, you shouldn't leave it in the circuit. And maybe it drifted in value and they were trying to compensate for it or calibrate somehow. But yeah, this is going to need to be taken care of here. I'm going to just look at this close for a second here. It looks like the trace on the board is okay. I don't see any damage to the trace. So this wire right there, it looks like they were just trying to extend the connection from this pad over, but the trace looks okay. So definitely a number of things that are going to need attention. Looks like it's going to be time to start replacing some resistors in here. What I can do is get this zoomed out. Let's take a few measurements and see where we stand on some of these resistors. Move this over here, you can see that. What I'm going to do is just reach around on the other side, grab my test probes right here. Okay, so we're in auto range, that's fine. And I've got the schematic and this parts view. So I'm going to use this parts view right here. And it's a little bit faint, a little bit hard to see, but it has the resistor numbers that are located around on the board. So I'll just start over here and kind of work through some of these resistors, and then I'll compare them to the resistors on this schematic right here. And let's see where we stand on some of the values. Now they're in circuit, and some of these might be affected by resistors around them. So, some of the values might be off a little bit, but let's just kind of get an idea of kind of where we stand. Just set that. Yeah, just leave it on the resistance mode there, it'll be fine. So get that touched up there so you can see the screen. All right, so let's start over here. So this is R8 right here. And if I can find R8 on the schematic. So R8 should be 5 megohms. Pretty close. I'll have to go through these resistors and see if they're in tolerance and everything as well. All right, so let's take a look here. The next one says is R30. So what do we have for R30 here? R30. R30 is supposed to be 1.25 megohms. Pretty close. The next one, R7, right here. So R7 is supposed to be 4 megohms. That's very close, 3.975. That one's probably fine. The next one right here is R29. That should be 1 megohm. Pretty close. Is there one hiding under here? Yep, right there. So the next one over, it looks like that's R6, 800K. Yep, pretty close there. I can see this one right here. This says 200K. I can see the marking on it. Yeah, 200K, but yeah, the tolerance might be off a little bit on that. Next one after that, let's see, this is the third one over. Looks like that's R5, 150K. Yeah, that's a bit high there. The next one after R5 is R27. R27, 37.5K ohms. A little bit high. This next one, looks like that's R4. What do we have for R4? Where is R4? There it is, 45K ohms. Yeah, that's close. Pretty close there. This one right here, looks like that's R26. Where is R26 hiding here? 7.5K ohms. Not too bad. This one, this isn't going to test good because it looks very overheated. It's R12. What was R12? R12. Oh, R12 is a current shunt. Yeah, it makes sense. It's a very low value. R12 is 0.468 ohms. 0.468, if I can find the 0.468. Yeah, I mean, it's reading low, but it's high, so. It's not open, though. It didn't burn open. There's continuity through it. And it makes sense if this is a current shunt, and then there's that 15 amp fuse, so this gets back to that idea that 15 amp fuse maybe wasn't protecting, and this is what ends up happening. So you definitely get an overload and some other damage. All right, after that, let's see here, we've got R13. R13 is probably going to be another current shunt. Yeah, R13 is supposed to be 2 ohms. Not really getting a very good connection there. There it is. Yeah, 2 ohms. It's pretty close there. Looks like R14 is this next one. Yeah, R14. R14 is supposed to be 22.5 ohms. Well, it's an open circuit. A problem there. So this is an open circuit. There's no continuity at all there. That next resistor is R15. R15 is supposed to be 238 ohms. So this is the guy right here. Yeah, 238 ohms. That's fine. And R16. What do we have for R16? R16, where is R16 hiding? R16, 11.2 ohms. Oh, that's not looking right. So that's definitely a problem there. 30k ohms, wow. R16, yeah, that's what it says, R16. R16, 11.2 ohms. Wow, that is way off. Yeah, definitely a problem on that. So these two resistors that are a carbon composition type, looks like that's R17 and R18. And R17 and R18. So R17 is 1.109K. 1.109K. Well, this is just a 1K ohm resistor. It's brown, black, red. Yeah, so it's not even the right resistor, and its value isn't that great. And this one here is supposed to be, what was that other one? R18, 123.57 ohms. 123.57, so it's 123, so it's amazingly close to there, but they obviously want that resistor to be a very specific value, 123.57. These two down here, so this is supposed to be R19, and R19, what do we have for R19? R19 is 17.55K. Yeah, it's in the ballpark. And this one had that parallel resistor, so who knows what we're going to see here. This one is supposed to be R20, and R20 is supposed to be 113.77K. So let's see here. Whoa, that's way off. Yeah, R20, 113.77K ohms, 53K ohms, so that is not even close. So this may be off because of this parallel resistor, but you know, this could be a huge reason why things are out of spec. And actually that, yeah, R20 though, that's actually in the resistance setting right here. If you look on the schematic, again, I'm going to go over the schematic, so we'll look at all this a little bit closer and how these circuits function, but that's this resistor right here that's used on the last position of the switch. So that's the highest ohms position, and it's way off. So let's see, oh, there's these two resistors right here. Let's take a look at those real quick. And I think those are in the AC circuit, R23 and R24, R23 and R24. Yeah, they're on that modified bridge. They're supposed to be 4 k ohms, so let's see here. Yeah, they're short of that. That's not right. Oops. That one's closer. Yeah, but they're definitely not a precision type resistor, not the right kind for this circuit. Let's take a look at those diodes. So I'm going to go over here to the diode test mode. So let's go here. So these should be germanium diodes. That looks okay. 322. Go the other direction around here and open. Okay, so that diode is okay. Then it's this way here. Yep, that looks okay there. Reverse the polarity. And it's open. So the diodes look okay. I think they are, working the way that they're supposed to. So definitely looks like it's a lot of resistors in here that are going to need some attention. There's definitely a lot of issues going on, and these potentiometers should be tested as well. But yeah, it looks like it's going to be repairable, but it's going to need some attention in here. So now the question is what to do about getting these resistors. I think I have parts 260 meter that I salvaged a board out of. I don't recall if it's this Series 6 or not. So I'll have to go through my junk boxes and see if I still have that board and then what series it may have been from. So I'll have to do some checking around and see. If I don't have that, then I'm going to have to try and source these resistors. And as you can see, some of the resistors are some rather unusual values, and that could make finding them a little bit tricky. Now you can make a resistor by paralleling several resistors, parallel series combinations. Not ideal. Electrically it will work, but it could get a little bit unsightly on the board trying to stack up resistors and make the right values. So I'm not really wanting to go that route. I'd like to find the correct resistors, and if I could salvage them out of a parts unit, that would be, an ideal way to do it. Oh, that current shunt under here, already measured that. Yeah, that's this bar. Looks like right here. It's a real heavy looking bar. This has a very specific resistance right under here. It goes to the other side, but it looks okay. Yeah, it's fine under there. There's also a resistor. Check this. It's right down in here. It's kind of hard to see. You can see it right there, right above my finger. Do you see that? It's right there. So it goes from this terminal to, so these two inner terminals right here. Carefully set this area. These two terminals. And it should be a 15 k ohm resistor. So it's the 1 volt multiplier. So let's take a look at that and see if that's actually 15K. Yeah, it is. That's very close. That looks good. So no problems there. All right, let me grab the schematics and I'll go through how the circuits work in this meter. So if you're trying to repair one of these meters and want a better understanding of how the different circuits function, I'm going to go through the schematic. We'll go through DC voltage, AC voltage, the current measurements, and so forth. So let's get started on that. Here's the schematic for the Simpson 260 Series 6. Now the majority of meters in the 260 series are all based on the same circuit and the same operating principle. So if you're working on one of the other series of 260 meters, what I'm going to cover here would apply to those meters as well. Just keep in mind there are minor changes along the way. For example, this meter tops out at 1,000 volts, but previous series of these meters measured up to 5,000 volts. So a different multiplier resistor was used. So some minor changes along the way, but the basics of how the circuit functions remained unchanged. All right, so taking a look at the schematic, just a couple things to note before I start. Where you see these dashed lines, it just means that these switches are all ganged together and move in unison. So same thing down here with these switches. And this switch right here that has 5 positions and these have 12 positions, it just means that nothing happens on this switch after this 5th position. All right, so when these are moving down here to the other positions, nothing else is happening over here. And down here, this switch has the positive DC and the negative DC, that's just a polarity reversal on the switch. So I'm not going to go over that every time we look at this part of the circuit. It's just implied how that functions. And the point of that is that you can have the common positive and then the positive input can become negative. So again, just a polarity reversal. All right, so taking a look, this is the DC voltage measurement. So starting with the positive input, comes up here, come over here, through this switch, through this point right here, over here, comes up through this common part of the switch. And let's assume that the range position is where it's shown in the 500 volt and 1000 volt position. And in future schematics as I go through, when this position is down somewhere else, I'll put a little yellow line just to remind us that this is in a different location. But again, for here, we'll just use it in this top position. So this goes over here to the multiplier resistors. In this case, the highest voltage range, all of these multiplier resistors are used, so they're all in series. This 45 k ohm resistor is always in series as well. Comes over here, comes up here. You can see this is joining across here, but it wouldn't matter if this was down in one of these other positions. It's just jumping to the other side. And right here, note that this wire comes off and comes down here. You'll see that in other places as well, and we won't look at that because that alternate path doesn't go anywhere. It has no purpose for this part of the measurement. Okay, so don't be confused by other parts of the circuit that branch off because, again, they have no purpose to this measurement. So it comes over here. Here's the main meter movement. This is about 48 microamp full scale deflection, and then about 2 microamps goes around the meter, so 50 microamps total, and this is done in calibration. And then this 5,000 ohm potentiometer is set so that the total resistance from this point to this point is 5,000 ohms. Okay, so 5,000 ohms across here is 50 microamps and 250 millivolts full scale deflection. And this calibration is very important because if this is off, then it's incorrect for any of the measurements that the meter can make. So this calibration is very, very important. So again, the path comes over here, is joined to the other side, comes down here, and through the fuse and out to the common. So that's the basic path for DC voltage measurement. And before I forget, right here, this is the multiplier resistors for the high voltage input. So if this is on the 1000 volt input, down here for 1000 volts DC, it comes in through the 2.5 megohm resistor, through the 7.5 megohm resistor, and now you've just joined right here where it was, for the positive input. So it's just adding some additional resistance in series with these multiplier resistors. All right, so taking a look at the DC positive 1 volt, 250 millivolts, or 50 microamp input, you're using these inputs over here instead. You can see on the 50 microamps or 250 millivolt input, come over here, just comes directly to this side of the switch, comes right up to the meter, through the meter to the other side, down into common. So this is the most direct input you can have to the meter, the most sensitive position. And if you use the 1 volt input, it's just adding a 15 k ohm resistor as a multiplier resistor, joins right back up here, and the path is the same. All right, so taking a look at AC voltage, a little bit more complex because we have this modified bridge rectifier over here. This meter cannot respond to AC voltage. It can only respond to DC voltage. So we need some diodes to rectify or change the AC input to a DC input. Now I put a positive and a negative symbol right here, and we'll just look at this circuit in 2 parts. This is the part that brings us to the positive and negative voltage at these 2 points. This meter in the AC voltage measurement, this meter is across this part of the bridge. Okay, you can think of it as being across there. That's where this line and this line are off to, but we'll look at that second. So starting with just what we have here, you have the positive input coming in right here. The multiplier resistors, if you're using the 1000 volt input on AC, you're only using the 2.5 megohm resistor, comes over here. It's not using the 7.5 megohm, and then this would join to the same part right here. Comes up here, over, right here through this range selector. So let's assume it's up here in the highest voltage setting. You have all of the multiplier resistors in series. Come down here, another resistor in series, calibration potentiometer in series, and now we're at the 2 rectifiers in this bridge. So again, these are converting the AC voltage to DC. So this portion or this point right here is always at a positive potential, and this point is always at a negative potential. So when you have the AC waveform, the positive swing conducts through this diode blocks the positive swing. When you have the negative swing of the waveform, this diode conducts, this diode blocks. Okay? So then the path joins together right here, comes down, over, to the fuse and out to the common. Okay, so that's part of this AC voltage measurement. And again, this part of the circuit brings us to a positive voltage here, the negative voltage right here. So taking a look then at the second part right here. So coming from this positive point right here, come down through this calibration potentiometer, comes over here through this switch, so this would be down here in the AC voltage position, over here, comes up to this point, over here, this is going to be down here in one of these positions, perhaps up here in the top, but down all the way to 5, so somewhere in this area right here. It brings us to the other side through the meter, and this, again, this is 5,000 ohms across here. We come down here, so we're actually not going to the other side. Okay, we come down here to this point, over here, down, over here, and to the negative side of the modified bridge. So that's the path that puts the meter across this bridge. All right. All right, now let's take a look at DC current measurement. So it's important to remember that on DC current, the meter is placed in series with the circuit that you're measuring. So what essentially happens is the current flows through the meter, there's a shunt resistance that the bulk of the current passes through, and a voltage is developed across that shunt, and that voltage is what's measured by this meter. So of course the bulk of the current is not flowing through this delicate meter. All right, so what actually happens is that the current flows from the positive input over here, comes up all the way over here. For this example, let's say you're measuring 100 milliamps full scale, so you're on position 7, so this is joined right here. The current comes over here. Now we have two ways that the path we can go right here. So let's go to this top portion first. So the current flows up this way, so that's a 2 ohm resistor, comes over here, comes down through this very low value resistor, over here, through this low value shunt resistor, over here, comes up to this point. Now remember position 7 is joining, so it comes across here, comes down, and back out to the common. So that's the path that the bulk of the current is taking, okay? And these resistances that we're going through are making the shunt resistance. Now the other path right here, come down here, we have a 22.5 ohm resistor, come over here. So there's a voltage that's being developed on here, and that voltage comes over here through this, because this is joined on position 7 right there. So it comes over here to the positive side of this meter, the other side, and now we come down here, and this part right here, this is joined together, and this is all coming down here to the common portion of the circuit, and we've already been here at that point with the path that we were following. So essentially, you can see that this meter is just placed across this shunt resistance, and the voltage that's being developed on the shunt is then causing deflection on that meter. So if you're on the different ranges here, essentially it's choosing different combinations of these shunt resistances, and the resistances that are not being used for the bulk of the current that you're measuring become part of the circuit that is for this meter, okay? So all of these resistors are still in play. Now let's take a look at what happens when you measure the higher current for 10 amps. You can see that circuit right here, you would use these jacks on the front panel, and the current is just flowing like this, so a very simple path. And this is a very low value 0.025 ohm resistor. So a very low value, but a little bit of voltage is developed, of course, on that resistance. So I think I have here, yeah, the schematic, I narrowed it down just to the 10 amp setting, and you can see what happens on 10 amps. The voltage that's developed on this shunt, although it's very small, it's just enough to drive this meter, and that voltage comes over here, comes up here, over here, over here. We're in position 8 because you would select position 8 for 10 milliamps or 10 amps. Comes over here, through the meter, down, and then we return back here, and we're back to the other side of this shunt. Okay, so that's placing this meter across this shunt. So there's a position on the front panel that says transit, And what's happening in the transit position, it's just putting some resistance across this meter to help dampen it when the meter is moved around, and it keeps the needle from swinging wildly around. So the reason that that works is because you can think of this as a little generator. You have a coil of wire that's in the meter, and you have permanent magnets around it. That's just simply how the meter is constructed. So when the meter is trying to move, it will develop a voltage across the meter. So you can take a panel meter, and if you put a voltmeter across it, and physically take the meter and move it back and forth, you'll get a voltage out of the panel meter. So same thing would happen here. But if you put a resistance across this meter, same thing as what happens with a generator, it takes power because now current is flowing. So even though this is very small that's coming out of here, the power that it takes to cause any current to flow is enough to dampen the meter movement. So the actual circuit that's happening when this is in the transit position, if we start here as a DC voltage and go back, because let's say this is what's generating the voltage, you would come over here, come down over here, through this, so here's our resistance, more resistance there, a little bit more resistance there, come back over, and we're on the other side. So essentially, this resistance that we have is across this meter, and again, it just helps to dampen it so it doesn't move so much. All right, and the final thing to take a look at is the ohms or resistance measurement function. So if we look at the schematic right here, there's a 1.5 volt D-cell battery and a 9 volt battery. So the 1.5 volt battery is only used in the R times 1 and the R times 100 settings, and the 9 volt is used on the R times 10,000 settings. And you've probably noticed the batteries are only used in this ohms function or resistance measurements. Everything else about the meter is a passive design. It doesn't require any power. So it's easier to understand the resistance measurement function if you start with the battery and then work from there. So starting on the positive side of the battery, let's assume we're in the R times 1 position. So this is in position number 10 right here, and that'll be the same thing across here. So we have positive voltage right here from the battery, comes over here, comes down here through this switch, then comes out the positive terminal. And from the positive terminal to the common is the resistance you're trying to measure. All right, so current flows over here, comes back up this way, comes over here, comes up here through this switch. Now this is joined right here, so not coming up here, we're going right here. Comes across here. We have two different paths we can take, so let's go down right now on this path. We'll look at this in just a second going up, but coming over here, comes down through this resistor, through this 0 ohms adjustment, that's the potentiometer with the knob on the front panel. Comes over here, through this position right here, comes up here, through the meter, come down here, comes over here, comes to this point, down here, and now we're back over to the negative side of the battery. So that completes that path. Now when we were over here, this could also go up this way, and you can see what happens. It comes up here, and we have 11.2 ohm resistor, and then it comes right back down, and this is the common point right here, and we're back to the negative side of the battery as well. So the current can flow two different paths right there. So that's essentially the path that is used for the ohms measurement. And the different ranges right here, when you're selecting R times 1, times 100, and times 10,000, you're selecting the batteries right here. And over here, you're selecting the different multiplier resistors depending on where this is set. So this concludes part 1 on the Simpson 260 Series 6 repair. So it looks like it's time to start going through my junk boxes to see if I can locate some resistors to bring this meter back to life. Now, if I don't have the resistors on hand, then I'll have to see what other options I can come up with. Alright, so if you enjoyed this video, you can let me know by giving it a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. And stay tuned for the part 2 video on this Simpson 260 meter repair. As always, thank you for taking time to watch. And until next time, take care. Goodbye for now.